Not only does science move on, but people move on, and I'm generally heading towards the Liverpool end of this conglomeration. Very pleased to be doing so, and I both hope and expect that this whole venture will be one of a number of things that strengthens the Manchester-Liverpool axis of research strength in the north of England. Now, page down, Ian. Page down. There we are, thank you. Okay, observational data are always noisy, and what that means is that when you try to use them to make predictions, those predictions are always uncertain. And to paraphrase the great John Tukey, late and great John Tukey, it's better to give an honestly imprecise answer than a dishonestly precise one. And so for that reason, the fundamental tenet of prediction in my world is this one echoed by Peter McCulloch, that the answer to any prediction problem is a probability distribution. People don't like that because they prefer simple answers, but sometimes the honest answers are not so simple. I'm going to try to convince you of the wisdom of that with 3 stories, and the first one concerns renal failure. Now, in most cases, kidney failure is the culmination of a long degenerative process which is asymptomatic for many years. And if you've ever seen a patient admitted to a kidney ward who thought he was healthy yesterday and is now told he needs a kidney transplant, you'll realize it can be quite a traumatic experience. Now, whilst in most cases you can't reverse kidney failure, you can slow its rate of deterioration. And given the shortage of transplantation resources in this country and other countries, that's a very helpful thing to be able to do. But the problem that you see in this picture is that if you measure or attempt to measure renal function biochemically, it is rather wildly fluctuating. So if you focus in particular on the black graph there, those are successive measurements of renal function from a patient who would appear for some time, several years, to be losing kidney function rather worryingly, but then suddenly has a reversal and then another decline several years later. And so the real question that a statistician would attempt to ask of data like that is, there's some signal there, a word that Ian's already used, there's some noise there, and our fundamental task is to extract the signal from the noise. And that's one way of doing it. The dashed lines are my best guess at what that underlying signal is. But how do I know that those smooth curves, the dashed lines, are a good or a bad estimate of the underlying signal? Because basically any fool can draw a smooth curve through data, but risking a charge of arrogance, it takes a statistician to draw the right smooth curve through a set of data. And more to the point, I could also tell you, although it would complicate the slide, so I've not put it on the picture, how precise, or more realistically, how imprecise those smooth curves are. I don't believe they're the right answer. I believe they're in the middle of a range of right answers, and I can quantify how wide that range is. So if I want to help kidney physicians decide when a patient really needs to be referred to secondary care for expert treatment, for specialist treatment for renal failure, as opposed to continuing to be monitored in primary care, which all these people were being done. These were all patients who were being monitored in primary care. None of them had been identified as needing transfer to the renal unit at Salford. These are data from Salford Royal Hospital. What should we do? Well, let's focus on one patient, not one of the ones I showed you previously. Here's a rather longer trace. The upper panel shows us measured kidney function for one patient in primary care over an 8-year period, rather emphasizing the instability in the raw data. So what's the bottom panel? Well, the bottom panel was computed, each dot was computed in real time, meaning that wherever there's a dot on the bottom panel, the only data that's informing that dot is the data before that time. Okay, so I don't get to see the whole data trace. I'm working in real time forward, and I'm starting with a 50-50 guess that this person is losing at least 5% of kidney function per year. Why 5%? Because that's what a clinician tells me is an appropriate level at which they should be referred to specialist care. And clearly, I can't make any useful information without any data. But as I accrue the data over time, those probabilities fluctuate around the 50-50 mark for a few years, and then they increase quite clearly, and they fluctuate around a much higher level of around 0.7 or more. And that's the only way I know honestly to answer the clinician's question, should this person be referred to secondary care? Because actually, I don't think I can answer that question. What I can answer is the question, how likely is it that this patient meets your criterion, the clinician's criterion, for referral to specialist care? And what you do about that is a clinician's decision. As a statistician friend once said to me many years ago, before the good Dr. Wakefield did his work, when a friend at a dinner party said, as a statistician, what would you advise me about having my children vaccinated against measles? His answer was, as a statistician, I would advise you to ask your doctor. But one hopes that the doctor has been informed by a statistician about the evidence. Second story, NHS prescribing. The government, in one of its few sensible acts in the last 2 years, has made prescribing data available to anybody who wants to look at it. It's on the web, in an open website, and it lists each month the amount of every NHS prescription drug issued by every GP in the country. And here's a map of England showing you the rates in October 2011 for prescribing the recommended treatment for attention deficit hyperactivity disorder. And there's a lot of variation there, from 0 pence per patient per month to £2 per patient per month. And there's also a variation in colour, from blue is low and red is high. But of course there's a variation because data are noisy. So how do we know which of the pink and red patches indicate something important? So we need to decide what we mean by important. And here I confess I didn't have a clinician who was prepared to tell me. And so I decided that I'd like to isolate the areas that are highly likely, 95% is the conventional definition statisticians use, to be issuing at least 4 times the national average. And what you now see is 2 outstanding areas. And the one we know best is the one in the northwest, which is Merseyside. And so, informed by that picture, if you hone in on Merseyside, you see a rather remarkable picture. Now, those of you who know your local geography will know that most of the Wirral is fairly leafy and middle class, and substantial parts of the city of Liverpool are anything but. Now, whether indeed the good children of the Wirral are all suffering from attention deficit hyperactivity disorder and the equally good children of Liverpool are not, is a moot point. But there's a stark geographical difference in prescribing behaviour there, which I would have thought demands an explanation, even if the explanation turns out to be a byproduct of GPs' attitudes to ADHD prescribing rather than any genuine biomedical problem. And I don't think you would have noticed that if you'd simply been given a national map of the dots, because there would just be too many of them. And you need to separate the wheat from the chaff, or the signal from the noise. Third backstory. Current health surveillance systems inevitably only pick up a fraction of the true burden of diseases that are not generally life-threatening, because not everybody who feels ill goes to the doctor and does what they have to do in order to get their data onto an accurate system. But about 10 years ago now, I was approached by public health professionals in Southampton, in Hampshire, who were concerned that in particular the health surveillance systems operating at the time were really only catching the tip of the iceberg of foodborne infections. And furthermore, they were only actually able to confirm foodborne infections about 2 weeks after they were first reported by the patient, because of the process of samples being taken, sent to the lab, processed, coming back and getting into the information system. But NHS Direct was coming on stream at the time, and so what we decided we would like to do would be to look at again in real time, every day, at the evolving map of where people were phoning into NHS Direct for some combination of vomiting and diarrhea. So very non-specific, very broad brush. And of course, if you look at those circles on the map, and you know your English geography, you'll not be surprised to see quite a lot of circles at the head of the Solent, because that's where Southampton is. Ditto Portsmouth. And you don't get so many people in the middle of the New Forest. So again, just looking at the raw data isn't actually terribly helpful. And furthermore, and thankfully, the number of dots on that map, which is a 5-day window, is rather small. So in isolation, I wouldn't be able to say very much about whether there's anything unusual in that pattern of dots on the map. But over a 3-year period, you build up a lot of knowledge about the nature of the natural fluctuations in local incidence of this disease, and you can build a statistical model which is able to distinguish, again in a probabilistic sense, the surprising areas from the unsurprising areas, in the sense that the areas coloured red on the map there, on the day in question, which I can't remember what it was, I think it was March 2000 and something or other, were highly likely, again 95%, actually 99% for red, 95% for orange, highly likely to be showing a local current incidence at least twice what they should have been doing at that place at that time, right? Because these diseases vary seasonally. They also vary because of the demography of the catchment in different places, and you can adjust for that given historical data, and you can see where the potential interesting rises are. Now, I don't think a public health physician would get out of bed for a doubling of the incidence of non-specific foodborne disease because, you know, people do get sick from eating food and mostly they recover without any drama. So you might want to set a higher threshold. And of course, if you set a higher threshold, 4 or 8, what happens, of course, is that the red areas disappear. So again, I make the point here that what I can do as a statistician is to say how likely it is that a certain threshold has been exceeded, but I would require a clinician to make a judgment as to what the appropriate threshold was to trigger what kind of action. But the critical part of this approach, as opposed to the traditional surveillance approach, is that whilst it's very broad brush and very preliminary, and may reveal red patches that have an innocent explanation, okay, it happens in real time. It happens overnight with every day's new set of data. So, what do I hope to have convinced you of? That's what I hope to have convinced you of. It's almost always a mistake to believe that data are measuring what you want them to measure. And control engineers have long recognized that responding to every change in a system's output is a very bad idea. But I have to say that in my experience as a patient, most clinicians, and I really have the greatest respect for clinicians, I owe them my life, but in my experience, they do just that. They tell me that my creatinine has gone up, and that's bad, or it's gone down, and that's good. And it's much more complicated than that. Now, some people think statisticians muddy the waters by refusing to give a simple answer to what appears to be a simple question. I would argue that actually statisticians recognize that the waters are indeed muddy, and anyone who thinks otherwise is liable to delude themselves. But we know how to filter out the mud, and what we're left with is pure, clear water.